We are going to be working on our second lesson of Unit 10 today. So here we go. All right, I think I am all set. What are we going to talk about in Lesson 2? All right, we're going to basically get started here with just some terminology, some vocabulary. When we talk about square root functions, what are the pieces and the parts of it? Here in orange, we have the radical symbol, is what it's called here. Okay, this is the radical symbol. What we can do is put an index. Okay, an index says what kind of root are we doing? Are we doing the cube root? Are we doing the fourth root? Are we doing the fifth root? Okay, what is the root of the number that we are doing? If it's not written, if they don't write it, if we write something like the square root of 50 and there's no symbol there, I shouldn't call it a symbol, there's no number, it's simply going to be not really going to be a 1. It would be a 3 or a 4 or a 5. If there's nothing written there, we just assume that it's 2. Okay, so therefore, we don't write we don't write the 2 to say this is the square root of 50. Okay, that's what this is. This is the square root of 50. We don't have to write the 2 because the square root is the most common, I think. Probably why they do it. But if you happen to see something that looks like this with a little 3, okay, that's the cube root of 8. That's the cube root of 8. It's 2 times 2 times 2 equals 8, so the cube root of 8 would be 2. Okay, if you don't see something in that general spot, we're talking about the square root. Technically, we call that the index, as you can see in this box. Okay, the stuff that's on the inside of the square root symbol is called the radicand. Okay, that's important because you will see some, definitions or theorems or concepts where they talk about the radicand can be this or it can be that or that sort of thing. So all that's important to know there is the radicand, kind of a weird word, is what is underneath the square root symbol or cube root symbol if you happen to have a 3 here. Okay, or fourth root if it happens to be a 4. Okay, so this is some basic idea. Okay, a radical expression is simply an expression that has a radical symbol, this root symbol there, whether it's the square root or the cube root or the fourth root. If there is no index, it is implied that it's the number 2. We call that the square root. The radicand may have numbers, variables, one term, more than one term. Okay, there are lots of stuff that can be underneath there. We'll talk real quick about things that can't in the next slide. Okay, so these are all examples of some square roots. Okay, we're not really going to be dealing with cube roots and fourth roots and fifth roots in this unit. Okay, you're not really going to see that. It's important to know in the future that you could have an index there, but that's not really going to come up this unit. Okay, so this is the square root of 14. We could have some variables. We could have an entire expression where you're adding 2 terms together. Okay, this second one here has 2 terms underneath the radical symbol. This is one term, the 2g times d, but it's 3 different things being multiplied. Okay, you can have a square root that then is divided by a number. You'll see in our next slide that we can't have a fraction underneath the square root and call it simplified. Okay, we have to deal with that. What does this mean here? 5 next to the square root of 2. As you can probably guess, if we put x next to y and call it x times y, this is going to be 5 times the square root of 2. Okay, some people will call this, Mr. Forjohn especially, will call this 5 root 2. That's another way to say it, that's fine, but it's 5 times whatever the square root of 2 might be. Okay, and this one is the square root of 18. Okay, so there's some basic, what do these things look like? Okay, hopefully you're feeling good with that. Let's move on. All right, what does it mean? This is going to be a very, very big concept of this particular lesson is, what does it mean to be in simplest form? Okay, we can simplify lots and lots of different types of expressions. Okay, we would never leave 5x plus 2x as our answer. Sorry, that's why. If it says to simplify, because we can put that together. Okay, so there's rules as far as simplifying expressions. Okay, there are rules when we simplify square root expressions. Okay, what does it mean to be completely simplified? And these are our 3 rules. Okay. The radicand has no perfect square factors other than 1. Okay, perfect squares, remember, are 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. Okay, these are perfect squares. Okay, so we have to look for perfect squares inside the square root symbol. Remember, that's what the radicand is. Okay, the radicand is simply the stuff that's in here. Okay, the stuff that happens to be inside that square root symbol. Okay, so no perfect squares other than 1. It has no fractions. Okay, we have to split up any fractions. And there are no square roots in the denominator of a fraction. Okay, we'll practice these, but for now, this is the main idea. Okay, so for part A here, is this simplified? Is that example simplified? No way, because we don't really want to deal with fractions. Okay, this is a problem here. And there are some perfect square factors in some of these numbers here. Okay, remember a factor is just a number multiplied by another number. The factors of 18 are 2 and 9. So we kind of have to look for what are the factors of the things that are in the radicand. So what's the problem here? The first problem is I can't have a fraction. So why don't I split this up? Okay, this would be equal to the square root of 2 over the square root of 72 if I were to split it up. That doesn't really seem to help me that much, actually, because the square root of 2 isn't a perfect square, the square root of 72 isn't a perfect square. Maybe I could attack the beginning of this problem in a different way. Okay, isn't this 2 divided by 72 a fraction that I might be able to simplify first? Maybe that would be a better way to do it. So 2 divided by 2 and 72 divided by 2 would be 1 over 36, right? So that's the square root of 1 over 36. Now maybe I want to split it up. Wouldn't that be the square root of 1 over the square root of 36? And what's really fabulous about this problem is those are perfect squares. The square root of 1 is 1. The square root of 36 is 6. So that is my final answer. Okay, it looks a lot neater and a little bit nicer than what I started with up there. Okay, same thing in part B. How could I simplify these? And a lot of this is kind of PEMDAS type ideas that we've done before. Is there a way that I can put 3 squared plus 4 squared together? What would be the order that I follow? And how would I do that? Well, to me, I probably want to square 3 and square 4. 3 times 3 and 4 times 4. 3 times 3 is 9. 4 times 4 is 16. Now, I can put those together. And the square root of 25, well, this is a really nice problem because the square root of 25 is 5. It's plus or minus 5, technically. I think you'll see in this unit, often we'll kind of say the plus or minus is implied. You don't have to write it on every single problem. So that's another example where you can see we started with something that looked kind of complex and it was just 5 in the end. So we're just simplifying. We're putting things together that could go together. And each problem is a little bit different. So you just kind of, go back into your math toolbox of all the things that you know. What about part C? Example C. What could I do with this problem? All right, maybe this turns into something that I could factor. X and X, and this would be 16 is 4 times 4. And look at that. That is a perfect square trinomial, right? And what's cool is that this square root symbol and this 2 to the second power cancel each other out, right? So my final answer is just x plus 4, and I'm done. Okay, so many different things that we're going to be doing in this unit as far as simplifying, but the idea is can I make the problem more simple, which is the commonality through simplifying. Okay, so this is the idea of simplifying. Let's keep going. Okay, these are some more examples. Okay, a lot of these are very similar to what I just did in the previous slide. Why don't you guys try some of these? Okay, I'll fill in the answers and pause the video and come back. And there are 1, 2, 3, 4, 5, 6 problems, but they're not super hard. Give them a try. If you get stuck, come on back to me. I'll be working them out here. All right, I'm hoping that you're back from working out these problems now. If you're not, please pause me and come back. Okay, 1A, the answer is 8. All right, you can check that. 1B is 7. 13 is part C. And this last part here is simply 3 minus x. All right. The other pieces and parts of 2a and 2b, let's see if I can find those. I think that hopefully, I might have to actually go through these with you because I don't have an answer key with me, but that's okay because these would be good ones to talk about. It looks like we have 64 plus 15 squared is 225. Now I can add that back to 64. We get the square root of 289. Square root of 289 is equal to 17. Okay, so hopefully you got 17 for that one. This one, again, looks like a polynomial that will factor. Isn't that going to be, isn't that going to be x minus 3 squared? And this square and that square root will cancel each other out, and we just get x minus 3. Okay, so good job, folks. You're practicing. You're getting good at this. Let's move on to the next idea. Okay, in this idea, we're really attacking the first rule of simplifying. I can't have any perfect squares kind of inside the number that is in the square root, in the radicand, underneath the square root. So I gotta look for some perfect squares. This problem here, the square root of 24, isn't simplified. Okay, how could I simplify it? Well, inside of the number of 24, if there are numbers that I can pull out, I can take the square root of them, then I need to do that. And then I need to actually take the square root of them. And the reason that this works is, watch this. If you have a calculator handy, let's do this. If I do the square root of 50, if I do the square root of 50 and I just type it in my calculator like that, I get about 7.07. If I do the square root of 2, I get 1.141 more or less. And if I do the square root of 25, well, that's a perfect square. That's just 5. So why don't I multiply? I'll do this multiplication, and I'll get, if I multiply that out, take a guess. Any ideas? I get, you guessed it, 7.07. So these are exactly the same. The square root of 50 is the same as the square root of 2 times the square root of 25. Isn't 50 the possibility of breaking that up into 2 times 25? So I can break up the factors that are inside my square root symbol. Okay, the square root of a times b is the same as if I were to first find the square root of a, then find the square root of b, and multiply the answers. Or I could simply multiply a times b first, and then take the square root. Okay, so we're going to use that to our advantage to simplify here. The square root of 24, are there any perfect squares? Let's remember the perfect squares. 1, 4, 9, 16, 25. Are any of these numbers a factor of 24? Which one is it, guys? The 4, of course. So let's think about this. Instead of writing, and I'll do it green so it kind of stands out. Instead of writing the square root of 24, let's write 24 as 4 times 6. Okay, remember, that's the same as the square root of 4 times the square root of 6. I kind of split it up into 2 square root problems. And now, the reason, why the heck am I doing that, Ms. Prasher? Well, look at this. Because the square root of 4 is just 2. Okay, 2 times the square root of 6 is my answer here. Okay, we're looking to simplify. Okay, in the past, when we had to deal with the square root of 24, what did we do? Well, we just plugged it in our calculator, and we wrote the square root of 24 is equal to, okay, the square root of 24 is equal to 4.9, more or less. But that's kind of an estimation I had to round in my calculator. And to simplify an expression with a square root is to follow this process here. Okay, to take out any factors that are perfect squares. And this is actually a lot more accurate than this, because this one I had to round. And this one I'm writing, my final answer is 2 times the square root of 6. Or some people call it 2 root 6. Okay, those are 2 different ways to say that. Okay, how does it work with variables? That's interesting. How do I work with variables? Well, the things to remember is that the square root of x squared is x. Square root of x to the 4th is x squared times x squared. Square root of x to the 6th is x to the 3rd times x to the 3rd. So therefore, the actual answer here would just be x squared, or x to the 3rd. So Basically, when we deal with variables, we're looking for even numbered exponents. All right, we're looking for even number exponents. If I write this out, the same exact problem, if I write it out like x to the second times x times y to the second times y to the second. Okay, this piece here, oopsie, highlighter. This piece here is a perfect square, right? And so is this piece, and so is this piece. So what can I pull out of my square root symbol? Because it's a perfect square. Well, what makes x squared? X times x makes x squared. What makes y squared? Just a y. What makes another y squared? Another y. So what's the only poor little buddy who's remaining in here? The x. So the only thing that is remaining underneath the square root symbol is that one little x that's still in there. Okay, this is just want to make it really easy to see. Now this looks a little bit sloppy, guys. I want to clean this up a little bit. Instead of writing x times y, I'm going to write x y squared times the square root of x. And that is your final answer. Okay, that's simplified all the way. Okay, let me get rid of this because that was kind of in the way. And now, what about a combination of numbers and variables? Okay, what about a combination of constants and variables? Well, 48. Let's look at the perfect squares. 4, 9, oops, I forgot 16. 4, 9, 16, goodness gracious, 16, 24. 16 is kind of funny that it got highlighted because I think that's the one we're looking for, right? 48 has a factor of 16. 16 times 3 is 48. So instead of writing the number 48, let's write 16 times 3 times a squared times b. Well, what are perfect squares that come out of here? Let's do that in red. 16 is a perfect square, and a squared is a perfect square. So those can get actually we can take the square root of those. I can apply that. So 4, the square root of 16 is 4. The square root of a squared is a. All right, these guys, the 3 and the b, have to stay. They have to stay underneath the square root symbol because I can't really take the square root of those, without getting a decimal. So 3b. That is my final answer. 4a times the square root of 3b. That is the final answer for that one. Okay, you're looking for perfect squares that are underneath the square root symbol. Instead of writing, let's review. Instead of writing 48, we wrote 16 times 3. Square root of a squared is just a, so that can come out because I applied the square root. The square root of a squared is a. That's why when you pull it on the outside, you're just left with a. Okay, the square root of 16 is 4. That's why when you pull it to the outside of the square root, it's just 4. Okay, 3 doesn't have any perfect square factors inside, and neither does b, so they have to stay underneath. Okay, this is not an easy concept. Please feel free to go back and rewatch pieces that you need to rewatch. We will be practicing this a lot in class tomorrow, so don't get stressed, but please come to class with questions if you got them. Okay, this is called the product property of square roots. Our next and final slide, okay, so stick with me, guys, as our last slide, is dealing with quotients. Okay, the same idea applies. You can split a number into, two different options if you have a fraction. Let me look at it here. I think this is the best way to say it. The square root of a over b is the same as the square root of a over the square root of b. Okay, I can apply, sorry about the resolution here, I can apply this square root symbol and just put it on the a or just put it on the b. Kind of splitting up an entire fraction into two little bitty square roots. Okay, let's try. Instead of writing, and this might be a little bit neater if I write it more like this. Okay, instead of writing the square root of 12 over the square root of 27, wouldn't that be the same thing as the square root of 12 over the square root of 27? And now I can look for my perfect squares. Again, it might be nice, ladies and gentlemen, to have 1, 4, 9, 16, 25, 36. Some of those perfect squares written down somewhere on the side of your paper. Which one is inside of 12? Well, that is the square root of 3 times 4. 4 is a perfect square. What about 27? Any factors here that are Any numbers there that are a factor of 27? Hopefully you're saying 9. That's 3 times 9. Okay, when I take this and this out, when I kind of pull them out, I apply the idea of the square root. Okay, the square root of 4 is 2. So on the top, I have 2 times the square root of 3. On the bottom, I have, what is the square root of 9? 3 times the square root of 3. Okay, now what's cool here is, because I'm multiplying, these cancel. I have some square root of 3's that cancel each other out. So my final answer is just 2/3. Pretty cool, right? Okay, the same thing happens with some of these other examples here. I'm going to go through these quickly because I feel like the video is starting to get real long. So, square root of 36 over x to the 4th. I can split that into the square root of 36 over the square root of x to the 4th. These are pretty nice numbers to get us started as beginners. The square root of 36 is 6. The square root of x to the 4th is x to the 2nd. Why? Because x to the 2nd times x to the 2nd is x to the 4th. Remember how when we have common bases, we add? Okay, we add up those exponents to get the 4. So since you're going in the opposite direction, you're kind of looking for what numbers add to make 4. Would be 2. So 6 over the square root of x. I'm sorry, 6 over, my final answer is 6 over x squared. And then one more. We have the square root of y to the 6th over 4. Let's split that up into the square root of y to the 6th over the square root of 4. This is y to the 3rd, and this is 2. Okay, why is it y to the 3rd? Because y to the 6th comes from y to the 3rd times y to the 3rd. Why do you get 6? Because you add those two exponents together. Okay, so this is kind of how it would work with dividing, the quotient property. Okie dokie, and again, we can talk about that more tomorrow in class. I think we're going to stop there. If you would like, let's do this. If you'd like to try 3 more on your own, I will show you the answers to these in class tomorrow. How's that sound? Okay, so we have 3 more to try if you'd like, and we'll do some of the real world application as well. So pause the video so you can see the example problems if you want to try some more, and I'll see you in class tomorrow. Have a great afternoon.